Let's take another example of an induced EMF. In this case, we're going to look at the uh, rod that's being moved down a rail system. And so we have this rod moving to the right at a speed of 1.3 meters per second. So this is our velocity. And it has a resistance of this R is equal to 2.5 ohms. And the rail separation is 25 centimeters. The magnetic field is 0.35 teslas. And the resistance of the U-shaped conductor is 25 ohms at a given instant of time, because as this bar moves, then the resistance will increase because of the extra distance. So at some instant in time, we'll say here to here, this resistance is 25 ohms. We want to calculate the induced EMF, the current in the U-shaped conductor, and the external force needed to keep the rod's velocity constant at that instant. So we have all of our stuff given here. So part A, the induced EMF is equal to the magnetic field times the length times the velocity, and that's 0.35 Tesla times, well, 25 centimeters is 0.25 meters, and our velocity is 1.3 meters per second, and that gives us the units that we're going to need. So we calculate this up, and that's 0.114 Tesla meter squared per second is volts. So that's part A. Part B asks for the current in the U-shaped conductor. Well, this is just a series circuit. The way this resistance, the 25 ohm resistance of this U-shaped bar, and the resistance of this rod are in series. So my current is going to be equal to my induced potential divided by the resistance of the U-shape plus resistance of the rod and I calculate that out and I get 4.136 milliamps. And to find the force, well, we can just use the current through a magnetic field equation from chapter 28. So the force is going to be equal to, this would be the cross product if we had the force as a vector. It's the I times L vector cross B vector. Since the magnetic field is perpendicular to the direction that the current is flowing, then the magnitude of the force is just going to be equal to the current times the length times the magnetic field. Meters. And actually, I guess the proper way to do this would be 10 to the negative third amps times 0.25 meters times 0.35 Tesla, and that gives me 3.619 times 10 to the minus fourth newtons. Very, very small force.